Okay, so let's start. So today we are going to talk about something new. The topic is about how to find a regression line. So let me start with the picture. Here's an x-axis and here's y-axis. Suppose that you have dot data. It's a pair of xy data. And it seems like it follows some linear line. So you probably have seen this kind of picture that there's lots of dots and then one line that passing through, and people say it's a regression line. And you might wonder how they find this kind of line. So my question is, given such set of data, so it's a xy data. Let's say D is a set of data where I is from 1 to n. How can you find a line that fits to the data? So I want to find a line that fits the best to the data. So that is my question. So it seems like it's non-related to our material, the multivariable calculus, but it is really the heart. It contains the essence of what we're going to talk about in the first half of the multivariable calculus. To answer this question, we need to know what is the meaning of positive derivative, how we can apply the meaning of positive derivative, and how do we find the extremal and extremal points, and also how to use the gradient in gradient descent method. So let me first ask a question. How would you define that line that fits the best to the data in this case? So for example, you might have a line, lots of lines, any line, and you can define that this line fits the data or this line fits the data. But you know by intuition that this kind of line fits better than the other lines, right? So how would you define that fits the best to the data? How would you compare that the red line is less fitting to the data than this green line? So you can think this as a mini project again. So we did the similar thing with the graphing the function, two-variable function. And to answer this kind of question or to solve this kind of project problem, you have to split your question into detailed steps. So first of all, you have to define your problem concretely so that you can check you solve the problem. So just saying that fits the best doesn't solve anything. Even if you have an answer, you cannot check whether your answer is correct. So you have to define whether your answer is, you have to define the scheme that can check your answer is correct. So I want to define what do you mean by fits the best? So in other words, what line fits, how do we define the term fits the best. So defining this term means that you have to be able to compare two lines, and you have to be able to tell one line fits better than the other line, right? So you need some kind of value to compare these two. So there's a sub-question to answer this question. How can we define a, you can call it a value, or you can call it a property, or just, let's say, call it value, a value for each line that you might compare, you might say lower is the better or larger is the better. In any case, we have to define a value for each line that we can compare the fitness. So you narrow down the question. So how do we find a value that compares the fitness of the line to the data? So I didn't tell you what data is. So if you have a specific example of data, it might be easier. So let's give some example. What kind of situation do you have this kind of XY data? If you have seen this kind of picture, what was the situation in the context?
Hubble's law.
But I'm sorry?
Hubble's law, expansion of universe.
Hubble's law.
Yeah, the
Okay.
x-axis was the distance from the Earth or observer, this distance from the observer. Y-axis was, I think it was a velocity.
Velocity. Velocity of some planet,
for stars or nebulas, something like that.
Okay.
Yeah. So the velocity is proportional to the.
Okay. So it's a good answer. So I don't know anything about Hubble's law, sorry, but probably many students too. But I mean, I will just write that as a Hubble's law, and we don't really need to care about the deep meaning about the relation between distance and velocity, but I will just say simply a distance, and here we have a velocity, and we can safely assume that there is a correlation between the velocity of some planet or some cluster of planet or stars to the distance from the Earth. So if you forget about all the universe law, just think about there is a situation that velocity is correlated to distance, and these dots are measured by some method, right? So there is a strict rule, but the rule is coming from the observation. And when you observe something, you have to introduce a measurement, and a measurement has an error, right? So it doesn't follow exactly this line, but there's some error from this line. So what's your goal? How do you find the line in this situation that to fit the best to the data?
Maybe we know how to measure the distance between the line and arbitrary dots or points. So by using that law, we can measure all the distance between each point and line.
So Distance, so you mean measuring the distance from dot to the line. So what's your method of measurement of distance?
Then we can have, then if we add all the distance between the line and points, and we can have a full length.
Mm-hmm.
We can compare the length of two different lines.
Mm-hmm.
The shortest one is the one which fits well with the
Uh-huh.
dots.
So good idea. So the idea is that you want to compare the sum of distance from each point to the line, whatever the line is, and we set that as a value assigned to that line, and I want that value, which is the sum of distance, should be the smallest to fit the best. So my question is, what kind of distance you're going to use from data to the line?
The line that goes through that goes
The shortest?
perpendicular to the line.
Perpendicular to the line.
Yes.
So
Vertical.
vertical or perpendicular?
Vertical like
This line?
yes.
Okay, it's a good one. So why should we use the vertical distance instead of perpendicular distance? So this one is the vertical distance. We could have used the distance from the data to the line as the perpendicular distance, right?
I was trying to say the perpendicular line.
Or you're trying to say the perpendicular one, okay. All right. So that's a good one, okay. So it kind of makes sense because it should be smallest, the sum of distance should be smallest if it fits the best. So here's our answer, the answer to this sub-question. Find the sum of all distances from each point to the line and assign the sum as the value. The value is the value that we are going to compare of the line. So in our argument, the distance, you have to be more specific, is the perpendicular or shortest distance, okay? So since we don't know what I'm going to talk about in this case, because I'm not sure about what Sahaber's law do, but in this case, why do you think that the point deviates from the actual line? So if the measurement had no error, every point should be on the line, right? Why did it happen? Why did the points deviate from the line? Why did we observe this kind of point data deviated from the line?
Because the other structure line we make the error.
Uh-huh.
So the point is not in the line.
Right, so other factor that affects to the error, right? So if you're going to measure the distance deviated from the actual line, then it kind of tells you that the measurement of distance from Earth to our other planet also has an error, and also the measurement of velocity also have an error. So you can think that let me draw in a bigger picture here. So this is an actual line, or whatever data lies in. If you had a data deviated from the line, and we are going to minimize the distance, the shortest distance from the data to the line, then it kind of means that when we measure this XY data, it should be here. The actual data should be here. Let me put a tilde here. But the X measurement had an error, right? So this had an error in X, and this also had an error. All right? That's how we get this deviation, right? Now, do we have other idea to define the value assigned to the line to compare the fitness? Instead of defining as a sum of distance, shortest distance from the line, is there other method? Square the distance. That's a good one. Why do you think the squaring the distance?
If we choose the square the distance,
Mm-hmm.
we can find the line more
Mm-hmm.
accurate.
Accurately, or in other sense, efficiently, I guess. Because, so having a sum of distance is okay, it's a good one. And whatever the value is, let me call it P. So the value assigned to L, in this case, is sum of distance from the line. So it should be x minus, so xi minus xi tilde square plus yi minus yi tilde square. And the sum is from 1 to n. This is our function. And I want to find L that minimizes this value, right? So you see the sum of squares are a little bit hard to compute because later you will see that we have to take a partial derivative of these equations in terms of xi tildes and yi tildes, because xi tilde and yi tilde all depends on the characteristic of this line, so this will be replaced by some parameters. And if you have a square root, and some of those square root makes harder to take a partial derivative. So another idea is that you can, so let me put a mark here. So it's the first answer. Maybe the second answer is that we can take the sum of squares of shortest distance. So in other case, now we have a different symbol for meaning the sum of squares as from there, is we could drop this square root symbol here. So I from 1 to n, and xi minus xi tilde square, yi minus yi tilde square. Now it becomes a polynomial, instead of some square root sign, we simply have a polynomial and easy to take a partial derivative in polynomial. So it might be easy to compute in this case. And minimizing the sum of squares is same as minimizing sum of square root is same as minimizing sum of squares. So as long as it's minimum here, it should be minimum here in some sense, right? Or you can just compare two possible outcomes. Do we have other method of finding the minimum value that fits the best? So instead of taking the shortest distance from the data to the line, what if we take the vertical distance? So for example, if you have a line, the actual line, and the data was here, instead of taking the distance from point to the line, let's take a vertical distance. So here we have xi, yi. Now xi is the same, and yi has a true value, but the actual value was deviate from the true value. Sorry, so I have to make it different wording here. So it's a true line. So this is called a true value, and this is called the actual value. So what's the difference between these two cases? What kind of situation that fits here or it fits here? So here we don't take the possibility of having error in xi, right? So in the above situation, we had a measurement on both x data and y data. What kind of situation fits to this kind of error measurement? Only y is measured, right? X is an input that we put. There should be no error, no possibility of getting error. So for example, what kind of situation that fits in this situation? That you always throw the true xi's and only measure the yi. For example, I'm measuring the temperature at temperature today at 8 a.m. There should be no error, right? I'm measuring at that time, at that date. There's no error, there is no possible error, but the actual temperature measurement can be errored, right? I could have some deviation from what it actually be, or the climate changes at time to time. So at that time moment, I'm measuring the temperature. The observation should be different from what should be in real. So depending on the situation that your x and y data, sometimes this type of error measurement should be applied instead of this type, right? So here's a third answer. In the situation where x theta should have no possible error we can define the value assigned to the line as what? Sum of what? Right. Now, the similar thing can happen here. So we can simply add error from yi to y tilde, but in that case, this type data can be deviate above or below, right? So in that case, if you simply take the difference between yi minus yi tilde, then in some cases, the plus and minus cancels out each other, and it could have an error 0. And we don't say that we don't want to take the error difference to be equal to sum equal to 0. So we only want to take the distance from here to here. Then we have to take this absolute value, which means that you have to square root of the squares. And this type of absolute value, sometimes it's impossible to take the positive derivative because you see that the absolute value function is not derivative at point 0. So you might have a trouble when you're using the positive derivative to find the lowest value. So you could have a sum of square root instead of absolute value, just as we did in previous answers. Instead of taking the actual distance, we take the square of the distance as a sum. Okay, so there are 3 types of things that you can define. Which one you want to try? You want to try, or let's say, let me pinpoint the two things. You want to try this, or let me give other name here. So in this case, let's say, let's call it L. It's a sum of all 1 to n of yi minus yi tilde squares. We want to try this. So it's not just having a different method. It just applies to different situation. So in which situation you want to try?
I have a bit of question.
Okay.
Before trying, I wonder, is there any rigorous proof that the sum of square and the sum of the one that we eliminated square, the two case should have the same answer if the one that eliminated the square root can also, is there any rigorous proof that can show that the two case goes to the same answer?
So the question is, so let's compare this case. Is there a, so it kind of assumes that, do we have the same answer when we take the value as a sum of distance, absolute value of distance, or sum of squares of distance? The answer is no. You don't get the same answer. But it kind of gives you the defining the meaning of fitness. In both ways, you have a meaning of well-fitted line to the data. It's up to you whether you take the distance, sum of distance, or sum of squares of distance. It might be curious. I mean, I think it's interesting to make a code that compares the answer when you take the sum of distances or sum of squares, and which one follows best than the others. So I think it depends also to the type of data you're talking about.
Then you mean we can define the word fit by different manner of math, by using the different manner of math.
Right, you are just defining the meaning of fitness using various kind of equations, various formulas. And I'm not saying this one is the best or this one is better than the others. It's just a definition. Okay. But I just mentioned that the method we're going to use involves the positive derivative. So I would like to try the square sum than the distance sum. So there are a big difference. I mean, there's depending on the situation that our data, whether we have to take this type of sum or this type of sums. What do you want to try first? You want to try this one? I think good. That's a good one. All right. Now, let's talk about this one. We have defined the value that fits the best. Let's name that value. So I'm going to define my own definition. So given a line L, line L is a line that sits in xy plane. The value, and also we need the data, and the data D consists of xy. Let's say, although I used the xi tilde, yi tilde, this is what we don't know yet. So let me just replace this summand by d xi yi. What we know for sure is the xi yi, which is given in the data. And this is the shortest distance from the line, from L. And then the value which is the sum of these distance squares is called, what do you want to call this number? Just name your variable. What do you want to call it, this value? We should have a name for this because we cannot say every time this number as a value because value is just a noun. We need a pronoun or just the real name for this value. Do we want to call it SL, not real name? It's fine, but I was trying to say maybe you want to say this is the sum square of L, something like that. actual words. But you can just call it SL. It's fine. Just be more creative next time. Just, all right. And okay, so L is not given, right? So what's our step to actually compute this SL? We want to minimize this number SL, but L is not given. We want to find the L. So how do we parameterize L? So in order to find this, to compare the value of L for different lines, you want to differentiate the other lines and the one line to the others, right? So we need some parameter to assign that this line is different to this line, or how to define the line using some parameters. So how can we parameterize L? How do you parameterize line?
The line has to go through one point, and that is one effect. And also the line has a slope or direction.
Yes.
So maybe in vector we can write the line as like L vector is equal to point vector plus T direction vector.
Okay, that's a good one. So answer, let's say there should be another answer. So first answer is that this L is nothing but a line that parameterized by the parameter T, where it passes through the point vector. That line passes when T equals to 0 plus T times the direction vector V. So P and V are two-dimensional vectors. All right. So it's a good one, but I want the parameters to define a line as few as possible. So how many parameters do we have? I mean, how many defining parameters? The T is a parameter in this parameterization equation to L. What defines the line itself is P and V. How many parameters we need to define P and V? 4, right? So P and V are both two-dimensional vectors, and they're independent. So we have 4. We need 4 values to define the line, but not these 4 parameters defines a unique. I mean, there are 2 pair of 4 points, 4 values that defines the same line, right? So I want to make it fewer. I want to make the parameter that defines the line fewer than 4. What other method can you use to lower the number of parameters to define the line? Integral? Intercept, you mean?
수열 같은 거 할 때도 임의의 어떤 한 값을 구한 다음에 그
So we are talking about how to define a line using few parameters. The number of parameters should be fewer than 4. Think about the configuration of a line in the 2D space. How would you define a line? How would you just say this line looks this using fewer than 4? Have an idea?
Maybe 3 parameters.
How do you use 3 parameters?
The P vector is a point of x and y, and
Mm-hmm.
we can be the constant
V is constant.
to 1 parameter.
How do you make, you mean the V can be a vector in 1 parameter. How would you do that?
I think it is 3 is the slope
Uh-huh.
of the line.
I'm sorry, say it again.
V vector is the slope of line.
Slope of a line. If you use the slope of a line, you cannot make a vertical line. You cannot assign a value to the vertical line because you need infinity to. The slope of vertical line is infinity, right? But I think you're getting to the point. How would you make the vector V parameterized by 1 parameter? Because think about V is just giving you the direction. How would you assign a direction using 1 parameter? How would you point that the vector is pointing to 1 direction using 1 parameter?
Just like, well, in two-dimensional space,
Uh-huh. Uh-huh.
like when we concern about the single variable function,
Mm-hmm.
then we can depict the slope as a real value.
Okay.
Like 1 will be this way,
Uh-huh.
45 degree. So we can just think slope as we need 1 parameter to define slope because the meaning of slope is the y change of y over change of x. So that can be just only 1 single parameter.
Right. The slope is a single parameter to define the line, but it doesn't define the vertical line. You cannot have a slope for the vertical line. What's the slope of the vertical line? What's the slope of vertical line? It's infinity. Infinity is not a number. You cannot assign a number to the vertical line. So we're talking about the direction of the line, right? So directional vector is just parameterized by 1 parameter other than slope, right? What's the parameter that you call to point out the direction? Angle, right? Angle is the one. So you can reduce your parameter to 3 parameter if you take the angle, right? 1, 2, 3, right? Let's lower them more. Let's make it 2. So let's get rid of redundancy as best as we can do. So there is some redundancy here. We don't need all 3. We only need 2. Polar coordinates to where? P? In P? I think you kind of get it, right? So in P, you don't need both r and theta, right? In this case, you only need r. You see, here's a 2-dimensional, and let's say you have a line here. Okay. So what you need to define a line, so you need to know how far does this line is apart from the origin, right? So distance d, and you need to know in which direction this line is pointing at. So let's say maybe this will be our v, right? So so in fact, these two have 4. This one has 4 parameter. This needs a 3 parameter. So in fact, what I should do is that the line is depending on p, v, and the parameter is t. And this one has p, theta, and parameter is t. But now we need to know the distance d and the theta, which defines the direction, theta, to define the line. So line that defined by d and theta, and whose parameter t defines the points in this line is now. What's the equation? What's the parametric equation to define this line? So think about what's the angle here. So theta is this angle, okay? This is theta angle, okay? So we need the point P, the vector, distance vector P. And we know that the distance d, we only need to know the angle of this distance vector. We need to know this angle. What's this angle? Theta minus pi. Theta minus pi or pi minus theta?
Theta minus pi divided 2.
Let's see. All right?
Theta minus 90.
Pi over 2. I mean, this angle is same as this angle. This angle. Oh, it's yeah. Okay. So let's take that. So we have d cosine theta minus pi over 2 sine zeta minus pi over 2. That's P. And V is cosine zeta, sine zeta. So let's make it simpler. What's equal to cosine zeta minus pi over 2? Sine zeta. And how about here? Cosine or minus cosine? Minus cosine, okay. So minus cosine plus t cosine zeta sine zeta. Okay, so we have a parametric equation. What we have to do is to define this value depending on the parameter that defines the L, because this SL depending on the line, and line is parameterized by two values, d and theta. So our next question is how to express S theta in terms of d and theta, which defines L. So the way defined is this by this equation, and we want to express our value, the S theta. It has no name, it's just a symbol, using the two parameter, d and theta. How would you do that? So let's break down this question again. So first of all, we have a summation, but in the sum end, it's only taking the distance from the point and the line. So we need to know how to compute the shortest distance from a point, let's say xi, yi, to the parametric line L d theta t. So d theta is the parameter defining line L, and t is the parameter to this parametric equation, and blah, 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 what is in there. So this is our sub-question to answer the questions here. So here's the situation. So you don't care about xi and yi. You can just replace it as x and y. Here's the line whose equation is d sine theta minus or plus t cosine theta, comma, minus d cosine theta plus t sine theta. Okay. This is our parametric line, and we have point here. So I want to express, let's say this is di in terms of xi, yi, and every parameter. So the t should not appear here. T is just a number that points the point in this line. So di should be expressed in xi, yi, and d and theta. So how would you find di? Let's think about strategy to find the distance. So what we need to find first to find the distance between this point and line. What's your strategy?
We should find the shortest point from the line.
Right, you should find shortest point, the point that is in the minimum distance from this point on the line. So let's say this is x tilde and y tilde, just intermediate symbol. And this is defined by some value of t, right? So let's say this is when t is star, t star. So in order to find, if you know this point, then we're done. We just take the Pythagorean rule. So and also, in order to find this point, you only need to find t star, right? So how do you find t star now?
Maybe the T star has to satisfy
Mhm.
some certain condition, and that
Mhm.
certain condition is that we can think as a vector.
Mm-hmm.
Let's say I can see that notation exactly, but let's say that the distance between 2 points, the point one is that out of the line and one
Mhm.
is on the line,
Mm-hmm.
and we can have a vector
Mm-hmm.
that goes through 2 lines.
Right.
And if we take the inner product
Mm-hmm.
of that vector and the
Mhm.
vector that lies on the
Mm-hmm.
line, then they have to be 0.
Right. Exactly. So I was thinking you might think about taking the R equation in terms of t and then take the derivative and find the extreme and so on. But the better way is what Hyun-Gyu explained, is that you take the vector between 2 points and you take the vector in the direction of a line, and you use the inner product between 2 perpendicular vectors is 0. So what's the vector here? Let's say, let's give a name here. Let's say this is V and this is W. So V is the subtraction of the 2 distance vectors. So xi, yi minus xi tilde, yi tilde. Although this is the notation for the point coordinates, but I'm using as a coordinate vector too. So this is equal to xi are just the number. So and then minus d sine theta minus t star cosine theta, and yi minus minus d cosine theta and minus t star sine theta. Okay. How about W? What's W? Right. It's just the direction vector. It doesn't matter if I took this direction or that direction. So just take the cosine and sine. And I'm using the property that the vector v and vector w is perpendicular, which means the inner product is 0. So we have cosine theta times this thing, xi minus d sine theta minus t star cosine theta plus sine theta times yi plus d cosine theta minus t sine theta equals to 0. All right, let's solve for t star. So t star, we have a long coefficient here. It's a cosine square plus sine square. It becomes 1. I'm taking t star to the right-hand side, and everything is left on the left side. So we have cosine theta xi minus d cosine theta sine theta from here. And here we have sine theta yi plus d sine theta cosine theta. So we have these two cancels out. We only have these, and this one is 1. So t star is nothing but cosine theta xi plus sine theta yi. So we found t star to define the actual xi tilde and yi tilde. And let's plug into the equation. So di, let's say square, take the square, that's better, is first of all, let's take xi minus xi tilde. Xi tilde is defined to be d sine theta minus t star, which is cosine theta xi plus sine theta yi. And then what? Cosine theta. Is that right? Yeah. And then square. And plus yi minus. So it's plus d cosine theta. And t is cosine theta xi sine theta yi times what? Sine theta square. Let's make it simpler, can we? Let's make it simpler. So I want to combine xi parts in here. So it's 1 minus cosine square xi. And how about y? We have minus sine theta cosine theta yi, and we have minus d sine theta square. And this part, we have 1 minus sine square yi, and what about xi? So we have cosine theta sine theta xi and plus d cosine theta square. Right? So let's take the squares. So we have this one is sine square, and this one is cosine square. So we have sine fourth xi square plus cos. Maybe I should take the square on the first term and then the next. So how about squaring this one? So we have sine square, cosine square, yi square, and d square sine square theta. And let's take the pairs. First one, I take the first and second, minus 2 sine cube cosine theta yi xi, and plus 2d sine square cosine yi, and 1 and third, we have minus 2d sine cube xi. Okay, something will cancel out. Don't worry. Even if it's not canceled out, we are good because everything is in simple functions. So we have cosine fourth yi, and we have cosine square zeta sine square zeta xi square and d square cosine square. And let's see, we have 2 cosine cube sine zeta xi yi. And then 2/3, and we have minus 2d cosine square sine zeta xi, right? You have to check whether my computation is correct, because after I do all this computation, I just simply put that into code, and if it gets wrong, then I have to go through all the computation again. So please correct me if I'm wrong. So we have plus 2d cosine cube zeta yi, right? So let's make a cancel. Well, not maybe a cancellation, but let's use the trigonometric rules here. First of all, let's combine this one and this one, right? It becomes d squared. And also, I think we can combine these two, right? Probably, let's see. Maybe I can also combine these two, right? These two, and also I can combine these two. Okay, so there's some pairs. I cannot combine these two, so let's write down sine fourth xi square, cosine fourth yi. I think forgot the squares here, squares. And also let's combine these two because it has the same coefficient. Cosine square theta, sine square theta, xi square, yi square, okay? And plus d square. And how about this? We have combined, we can combine these two. Minus 2 sine theta, cosine theta, xi, yi, right? How about this? I can combine this with this. Plus 2d cosine theta, yi. And how about these two? I get 2d, in this case, sine xi. Can I simplify more? Well, it's not necessary to simplify more. It's just making a simpler formula just to be nice. I think this is as far I can go. All right, so his happens to be a long equation, but anyway, we had an equation in terms of xi, yi, theta, and d. All right. So think about real question. So question is, so let's go back to the question. What the main question is finding the line that best fits to the data. Data is given. So although I put it in xi and yi, these are constants, right? These are numbers. What we don't know is d and theta. We want to find d and theta, which defines the line which fits the best to the data xi, yi. So question is, how can we find the parameters d and theta? Yes. Oh, you can do that?
사인 4제곱 세타 xi 제곱에 코사인 제곱 세타 더하기 사인 세타 제곱 xi 그 항이랑 세 번째 항
네. 다 이거
부분을 칠 수 있어요.
combine all this.
사인 제곱 세타 xi 제곱 플러스 코사인 제곱 세타 yi 제곱으로 그 세 항을 합칠 수 있어요.
If you do this, that's what you mean, right? Is that what you mean? You mean combine these three terms into this square of this sum?
사인 제곱 세타 xi 제곱 플러스 코사인 제곱 세타 yi 제곱.
Square here?
Yes.
Okay. I'm sorry, and then oh, you mean combine this and this one. Ah, okay, right, you're right. Okay, so it's a good idea. We have, so actually you can get rid of sine square plus cosine square in that case. So we only have sine square, we only have cosine square, and we can get rid of this, right? Okay. Can we reduce it further?
We can combine that equation to
This one, right? Yeah. It's a good idea. Sine theta xi minus cosine theta yi square, and we have d square and okay, so it's 2d cos, so let's say minus 2d sine theta xi minus cosine theta yi. I think we can do further simplification, right? The square minus 2. So we have sine theta xi minus. Can you see this in the video? Okay. xyi and minus d square. Now it's really simple, right? It's good. Okay. So I want to minimize the sum of these squares for I from 1 to n. That's the meaning of best fitting in our definition. So how can we find the parameter d theta that minimize the sum? So S d theta. Now instead of writing L, I can replace it as d comma theta because this defines the L, which is the sum of these things. So we have sine theta xi minus cosine theta yi minus d square. So we started from how to find the best fitting line in our data, and we boiled down to the question to find the minimum in two variable function. You see xi and yi are constants. You only have a theta and d in the parameter. So this question is, in general, how can we find the minima or maxima of two variable function, so real valued two variable function. So here comes the graph. So in this case, we can draw the graph of two variable function in three-dimensional space. Let's say our graph looks like this. Maybe it has some more figure here. So here, where x, y, z are somewhere here. I don't care whether it's on the origin or not. It just be this is our graph. So how do we characterize the local maxima or local minima in our graph? So what's the geometric characteristic of the maximum point and minimum point? So I'm not saying the minimum and maxima is a global thing. It could be local. So these are the local maximum. These are the local minimum. What's the common characteristic of these points?
I think B prime and theta prime, let's say that B prime and theta prime is a certain point.
Uh-huh.
And that point is local minima or maxima if we substitute those values to the partial derivative of
Uh-huh.
theta and b. And if that derivative is zero,
Uh-huh.
derivative is zero, then we can say that the theta prime and d prime, that point is local minimum or local maximum.
Uh-huh. So Hengyu said that if you take the partial derivative in both variable and if the value is zero at some point, then that point is local minima or maxima. Why did you think so?
Well, that the intuitive came from the single variable function.
Uh-huh.
Well, in the single variable function, we find the differentiate of the function f,
Mm-hmm.
and then that will be if the function is continuous.
Uh-huh.
Also, if the function is differentiable,
Uh-huh.
then when the slope is zero, that point is local maximum.
Uh-huh. Right.
So, but in this case, we have two variables that
Uh-huh.
that relates to the
Mhm.
z-axis. So,
Mhm.
in this case, we have to concern both directions.
Mm-hmm. Right. So the idea comes from the single variable case that you can find the local maximum, possible local maximum minima by taking derivative. And if the derivative is zero, you can guess whether it could be maximum or minimum. So here, instead of a single case, we have two independent variable. So you have to analyze both direction, x and y direction, whether the rate of change is zero or not. So you see, if it's on the top of the hill, then in either direction, you should have decreasing value of the z. And also in the creek, in here, you have to have the rate of change should be zero. That intuitive idea is totally correct. So let me define some terms when we talking about this type of situation. So this is not my definition, it's a common definition in calculus. So let's given a function f, and is differentiable on some domain D. So let's say D is some subset in R2. Okay. And the point x0 and y0 is called a critical point. If fx x0 y0 and fy x0 y0 are both 0. So in that case, the local minima and local maxima. Actually, this is a property or theorem. Local minimum and local maxima is obtained at the critical point. So I want to emphasize that this is the this statement is rigorously not correct. It's oversimplified. So I didn't take account of the boundaries of the domain. But if I just take the interior of this domain in our functions, and if function is defined to be differentiable at every point, then the local minimum and local maximum is always obtained at the critical point where the partial derivatives are all 0. So if you take the boundaries in count, then you have to check whether there is a local maxima or local minima at the boundary. Okay? But I'm not taking account of that. We are not taking account of the boundary of the domain. So we're talking about the boundary situation later, but for now, our purpose is to find the local minimum or maximum for every d and zeta. So, well, the zeta is any numbers, but d is always positive numbers. So here's also there's a boundary situation, but d is when d is equal to 0, it's a special situation, special type of situation. So we can handle it in separately. So let's consider that our S is defined on every real number, entire plane, where only d part is the positive number. So I want to take the derivative of d and zeta and where we find the 0. Okay. So, by the way, I didn't explain why we have a local minimum maximum when the partial derivative is 0, right? Why is it? I mean, you already explained in the two direction should be changed to 0. There's another implication in geometric way. As I said, I'm differential geometer, so I always try to think in geometric way. So if you have so it's a remark, y extrema at the critical point in geometric view. So you see, if you have a maxima in a two-variable function, what's the tangent plane look like at that critical point, at that extremal point here? Parallel to xy plane. So it should have a normal vector parallel to z-axis, right? So normal vector is 0, 0, 1 if you normalized 1. So at the extreme, the tangent plane, but I didn't define what tangent plane is yet, but you know what intuitively it looks like. Tangent plane is the plane that barely touches the graph of the function. Should be parallel to xy plane, i.e. normal vector is 0, 0, 1. So let me a little bit deviate from our argument about the extrema. Talking about the tangent plane. How do we get the equation of tangent plane? So the question is, how do we get the equation of a plane in general?
By using two parameters.
Uh-huh.
Like the surface for plane vector
Uh-huh.
is equal to the point vector plus t. Let's say t and s is the real value and
Uh-huh.
parameterized curve. Then the plane vector is equal to point vector plus t times a vector plus s times b vector, and a vector and b vector is both lies on the same surface, the same plane. Then we can parameterize by using system.
Right. So let me write that as a question here. So how can we, how to find the equation of a plane in three-dimensional space? So I would say one answer. There should be many answers, as there are many many ways to equation or parameterize the line. There are many ways to parameterize or make an equation of a plane. So one answer is that take a point vector P. Let's say plane is say H. Let's say P, plane for P. P and two vectors V1 and V2 parallel to P, then a point in P, let's say point Q, or point vector Q in P is parameterized by so Q is P plus T times V1 plus U times V2. So which means that if you have a plane in 3D space, you have to point out where you're starting from. That's our, here's the origin, okay? So here's an origin, and here's the point vector P, and this is the point P. And if you want to point out where any point on the plane, you have to think how far you move from P to the direction of V1, and also how far you have to move in direction of V2, and the linear combination of these V1, V2 using the parameter T and U gives you the point, any point in the plane. That's one way you can parameterize. So you need two parameters because this is two-dimensional thing, which is the plane. How about the other method? So for example, you have an equation of a line like y equals to mx plus b. You have also equation of a plane, z equals to ax plus y, or ax plus by plus cz equals to 0, or d. Probably heard in the high school, right? No? Like you have an equation of a plane, something looks like this, right? So Okay. Right, probably it will come up later. We move on. Let me show you the way how it does, how it works. It's similar to this type of situation. Let's say I want to find out the coordinate of Q in terms of x, y, z, because it's in the 3D space, right? And I know where my P is. So let's say my P has 3 coordinates, x0, y0, z0. This is constant, okay? And what I do know is that I know what the normal vector is. Let's say this is norm n. And we have normal vector coordinate A, B, C. Now, let's take the vector P to Q. Okay. So let's say this is our PQ vector. Maybe PQ. Okay. So PQ vector is given by x minus x0, y minus y0, and z minus z0. Right? That's the PQ vector. And if you know what normal vector to the plane is, then the inner product between this normal vector and PQ vector must be 0. So n inner product PQ, which is A, B, C, norm, x minus x0, y minus y0, z minus z0 equals to 0. But let's compute this. This is A, x minus x0, B, y minus y0, C, z minus z0 equals to 0. So this equation, you can modify to this type of equation by taking D as AX0 plus BY0 CZ0. It's another way to express the equation or express the plane. Anyway, that's an aside side talk. And what was our goal? So we want to find out the theta and d that minimize this. We should take the partial derivative. Do we have time? We still have time. So let's keep this and try to take the partial derivative. All right. Let's take the derivative in terms of d first. So this is summation, so summation remains still. But for each summand is a square, so we're taking partial derivative as if it's a single variable function. So theta is a constant, so these are constant, and we only have d as a variable. So we have 2, it's a square, it's a quadratic polynomial, 2 sine theta xi cosine theta yi, and minus d. And if you take the derivative inside of the square, you get minus. So you get minus here. So let's combine. So now it's the sum of simple linear terms. So let's combine the xi's and yi's. So it's minus 2 sine theta 1 to n of xi minus a plus 2 cosine theta of 1 to n yi. And if you combine all this, then you get 2dn, right? So let me give a different name for this. I'm not going to write the summation notation for every time. This is the big X, and this is big Y. Okay. So then this is minus 2x sine theta plus 2y cosine theta and plus 2dn. I want this to be 0. And let's take the derivative in terms of theta as theta. By similar method, we have I from 1 to n and take the derivative for each summand. So 2 sine theta xi minus cosine theta yi minus d And what? Inside we have cosine theta xi plus sine yi. I think we need a little bit of more calculation. We have 1 to n of, let's go out of 2. Here we have xi square sine theta cosine theta. I think cosine, it doesn't cancel out. Okay. So let's write it all down here. So cosine square theta yi xi. And we have minus d cosine theta xi. And here we have sine square xi yi minus cosine theta sine theta yi square and minus d sine theta yi, right? Can I simplify anything here? Maybe I can simplify these two. Also these two. Okay, so let's take 2 of, it's cosine square minus sine square is a cosine 2 theta, right? So it's a minus 2 cosine 2 theta 1 to n of xi yi. And how about this part? We have same thing. So it's 2 sine theta cosine theta sum of I from 1 to n of xi square minus yi square. Okay. And what else? We have these two. So plus, it's actually minus. Minus, I have to write it separately, right? So 2d cosine theta xi minus 2d sine theta yi. All right. So I should give a different name for this. I cannot simplify more. So let me give this name. What kind of name should be? Let's say A. Okay. And let's say I want to replace this by B. These are all constants. And these already defined as x, and these are y. So we have two equations. One from SD equals to 1, SD equals to 0, which is minus 2x cosine theta plus 2y sine theta plus 2d n equals to 0. That's the first one. And second one is minus 2a cosine 2 theta, right? And how about the second part? We have, let's make it simpler. It's b sine 2 theta. I forgot. Oh, yeah, that's right. Yeah, and then minus 2 x d cosine theta and minus 2y d sine theta equals to 0. So we want to find the theta and d satisfying both equations at the same time. This one? Oh. 2x sine, I forgot, I take the opposite here. So minus 2x sine and cosine, right? All right. If it was cosine, then I could have just replaced here. It's not getting complicated, right? So I didn't make any mistakes so far, right? So given the data, we know what x, y are, and also n, a number of data. And we also know a, b, and so on. We have a trigonometric equation for theta and d, right? So okay, so one way you can find the theta and d is that you can substitute your d in terms of theta using the first equation into the second equation, and then make it into equation of theta, omni theta, and then find the zero satisfying find the root satisfying this equation. So one way to go. So question: how to find theta d satisfying two equation. First answer, just take the d from the first equation, which is 1 over 2n, 2x sine theta minus 2y, 2 cancels out, right? So x sine theta, y cosine theta, and then plug into here. So it's minus 2a cosine 2 theta plus b sine 2 theta minus 1 over n x sine theta y cosine theta. So I place d here. So and there's a common 2's here. So we have minus 2 taken out, and we have x cosine theta and y sine theta. And I want this to be 0. Now it's equation of theta only. Can I make it simpler? Let's try to take the multiplication here. So this is equal to minus 2 over n, and we have x sine theta, x squared sine theta cosine theta, minus y squared sine theta cosine theta, right? And then what? We have xy sine square minus cosine square. So minus xy of cosine 2 theta. Okay, should be equals to 0. I'm trying to make it simpler, as simple as possible. So just trying to make it more concise. So it's 2a cosine 2 theta, and it's b sine 2 theta. So I didn't mess up with the equation, right? So is there any mistakes. I'm not sure why n appears here. Is it correct? So if nothing is wrong, it's okay. Just appears here. And let's take here minus 1 over n times 2 times sine cosine. It's a sine 2 theta. So it's a nx squared sine 2 theta. And also here we have minus y squared sine 2 theta. Okay. And here we have what? Plus 2 over n xy cosine 2 theta. I think we are getting in the right direction because
I think we changed the, I think my, I mean, the fourth equation,
1, 2, 3.
the last one, the
Uh-huh.
fourth equation is, I think, going to be plus.
Oh yes. Oh, wait. Okay. Has a minus. This one is plus. Okay. Right. Plus. Right. Thank you. So let's combine cosine part. We have 2a xy cosine 2 theta. And let's combine sine part, which is b minus 1 over n y squared x squared, or x squared minus y. Yeah. Minus x squared minus y squared times sine 2 theta equals to 0. Now we're done, right? We only need to find the theta satisfying this. You can take a tangent 2 theta if this is not 0. Okay. We can find any theta if you want to. If you take these coefficients as a coordinate of vectors, and the 2 theta is the angle that points to the vector which is perpendicular to the vector coordinates of these two coefficients, and so on. We can find theta. Okay, so once we found the theta, we can find the d. So d theta is now could be an extremo. Well, we don't know whether it's a local maxima or local minima. What's your guess? I think there should be only one value for theta satisfying this equation, and d is defined as one value depending on the theta. Right? So we only have one extrema as a critical point. Should it be local maximum or should it be local minimum? What's your guess? Choice is 2. Just pick one. Maxima. So we are trying to take d and theta, which minimize the sum of squares, right? Okay, we found the 1 by using all these equations. If it's maxima,
Then it has to be, it will be either convergent.
right, so if it's maxima, then if we deviate the value of d and theta from what we have found, it means it only decreases the sum of squares, right? Which means it gets more fitter than the before. So for example, you can think about the situation where in an extreme case. So here's the data, right? And if your line is very far away from the data, okay, so there's a d and theta defining these lines. What should be, how far, I mean, what should be the value of the SL? The sum of square, does it have to be large or does it have to be small if your line is far away from the data? Larger, right? So if you move your d theta from where you found as its extremal, it should be larger and larger if you deviate more and more, right? So which means that if your d theta, what you found is just one set of the parameter, then it should be minimum where it is fitting the best to the data, because if you diverge from this line, then it only increases, the sum of squares only increases intuitively, right? So also there's a way you can check by mathematical formula whether it's really a maxima or maxima or minima. But in our situation, it is clear that what we have found is the minimum, and it's the parameter that best fitting to the data. All right, we have a formula, we have a method.
Professor, I think we can, this is a purely technical thing, but I think we can more simplify that equation.
Mm-hmm.
Like x squared minus y squared is actually exactly equal to b, right? In our definition.
X squared, y squared is the square of this sum here. B, maybe, I mean, I think maybe, yeah. No, I mean, I think you have a point, but the reason why I worry about why I have an n is because I thought the value here is comparatively smaller than the value b here. So I'm not sure why this happened in here. But if it's not, if I didn't make any mistake, then it should be fine. So let's summarize here right now. So it's almost done here. I mean, I passed time. So we have found the equation. I mean, the main question was finding the curve fitting and the data fitting into the line. And we found the way to find the parameter, two parameter, d and theta, to define the best fitting line here. And the next time we're going to talk about how to simulate in our Go code. So we are going to talk about how to generate a random value as a data, and then how to find a curve fitting using our formula that we computed. And once we've done this computation, once we check that this works, what we're going to do next time, in the next step, is instead of getting the actual d and theta which fits the best, we can approximate d and theta from the random value to the actual value using gradient descent. So by gradient descent is the way how you can make the function value decreases the steepest. So you see that the value d theta is the parameter for the two variable function s. And my purpose is to minimize the value of s. So we want to find the way to minimize the value s by changing d and theta slightly. And the method is called the gradient descent. And that's the essence of the machine learning. So that's our next step. So next time we're going to do some Go coding. And before I finish, let me emphasize that I uploaded, so this is uploaded assignment yesterday. So there are two assignments. One is the partial derivative that we discussed last time. And also in the programming, we did in the class what I didn't actually did in the classroom to code in the Go language. So the purpose is defining a diff method, the diff function, which computes the differentials of a function. So differential is a matrix, so your output is the form of matrix. So you have to define the matrix too. Maybe we can encapsulate this task into our Go code simulation next time. But if it's not, I will do this programming task separately. But in the meanwhile, please go through the previous assignment for the programming, and then if you can't follow what is done, please ask anytime. All right, so let's stop here and then see you on Friday.